in this video we'll be solving this question, and the question says a metallic sphere shell of radius r1 carries a charge q1 concentric with its another thin metallic sphere shell of radius carrying charge q2, right? And we asked to find the electric field at the radius r less than r1. This is r1 and this is r2, and these are the metallic shell. This is one metallic shell and this is another metallic shell. So, and we are asked to find the electric field at the point r less than r1. So for r less than r1, what they mean is the point inside. It's the point inside the this very circle, at this point in here. That is what we're asked to do. But before we solve this, we need to bear in mind that one of the properties of a conductor, okay, remember they said a metallic sphere, which is a conductor, right? And one of the properties of a conductor is that the electric field inside the conductor is zero, right? Electric field inside the conductor is zero. Take for instance, if I have this a metallic sphere, or maybe a metallic conductor, so, and I decide to have this as the Gaussian surface. This is the Gaussian surface. The Gaussian surface. So, and for, if this is a metallic conductor, the charges out here maybe will be positive because the excess charges will be concentrated at this surface, right? So this is positive, 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 positive. Okay, let me change the color now. If this is a positive charges, right, and I decide to have a test charge here, Q1. So, and we already know that the properties of, one of the properties of a conductor is that the electric field inside a conductor is zero, right? It is zero because the charges does not move. They actually are the equilibrium. So if originally it is zero and I decide to place Q1, which is a positive charge in here, then what happens at this point? Will the electric field still maintain zero or not? So this is what they are asking us to do at this point in time. This is a metallic conductor, and you have a test charge in here, which is Q1, right? So since this is positive charge, one thing about the conductor is that if you place a positive charge inside, then the charges in this conductor will try to rearrange themselves. How do they rearrange themselves? This is positive. From the knowledge of electrostatic, we know that the positive charges attract the negative charges. So at this point, if this is positive charge, then there will be a concentration of negative charges within this surface. So these are the negative charges. All of them will rush in to neutralize what happened over here. So, and at the point they neutralize this charge, then you have that the net charge in here will be zero. The net charge is equal to zero, right? And if the net charge here is zero, so from the Gauss's law, we have that the flux E, right, is equal to the closed loop integral of E dA is equal to, or Q enclosed, that is the enclosed charge divided by the permittivity of the free space. So this is the Gauss's law, and we found that the Q enclosed in here will be 0, right? So if Q enclosed is 0, then we can easily infer that the flux is 0 and the electric field is 0. So for this first part, we can now say that E, which is the electric field, is 0. So, but there is an interesting thing that happened here. Now, the negative charges in here, they have neutralized the charge inside this, which is, I use this as an analogy. They've neutralized the charges in here. So at this point, you will be having like excess positive charges surrounding this part. Excess positive charges. This is positive charges. This is positive charges, positive charges. So, and if you look at this, it's the same thing we are having here. So at this point, you have the excess positive charges outside, right? So the next question, we're asked to find the electric field at radial point, this, right? So, and I think, let me clean part of the positive charges. Okay, so, and let me change the color as well, color of my pen. So in this case, we're asked to find the electric field at this point, right? That is, let's say, the point P, which is this, right? So, and for us to find the electric field, we have to first of all determine the enclosed charge. So the enclosed charge from this point P, we can easily say that this is positive charges, and that's positive Q1. So we can easily say that EDA is equal to Q enclosed divided by epsilon naught. So, but because this is a uniform charge inside, then we don't really have to go with this enclosed integral. So we'll be having that EA is equal to the enclosed charge. At this point, the enclosed charge is Q1, right? Q1 divided by epsilon naught. So, but remember, this is a sphere, right? So we have to use the area of a sphere at this point here. So we can say that the area of a sphere, and this is EA. At this point, area of a sphere is 4 pi r square is equal to Q1 divided by epsilon naught. So at this point, you can easily write the electric field. So we can say that our electric field E will be equal to Q1 divided by 4 pi r squared epsilon naught. So this is the electric field. And the next question, we're asked to find the electric field at the radial point R is greater than R2. Let me clean this box. R is greater than R2. Okay, let's come back to this as well, and let me clean this blue path. Let me erase it. Good. So remember, the electric field inside, or the net charge enclosed, is zero inside, right? Because the charges out here, or the charges in the metallic conductor, try to neutralize the charges inside, and thereby leaving the excess charges outward, right? But we as well have to like look at this same one. You get? So since we have the Q2 as well, so we'll be having the excess negative charges outward. I'm sorry, excess positive charges outward, because the Q2 is positive. We have the excess positive charges. This is a positive charge. This is a positive charge outward. Wow. Positive charge. Positive charge. And now, let me change the color of my pen as well. Now we asked to find the electric field out here. Let's assume this is the Gaussian surface, right? So before we find the electric field out here, how do we really determine the charge enclosed within this Gaussian surface? Remember, the inside here, we have the Q1 positive round, right? We have Q1, 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 Q1. Then at the outside, we have like Q2, 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 Q2. So the net charge enclosed will be Q1 plus Q2. So we have this to be Q1. Oh, let's leave this part, it's getting congested. So this will be using the Gauss's law, we have this, and the shape is sphere, which is 4 pi r squared, and the charge enclosed, the enclosed charge will be Q1 plus Q2. Q1 plus Q2 divided by the permittivity of the free space. So we have that the electric field E will be equal to Q1 plus Q2 divided by 4 pi r squared epsilon naught. So this is the electric field outside the sphere. Okay, let's look at the next question. In the next question, we're asked to find what are the charges on the inner and the outer surface respectively. Okay, let me see. Let me wipe this part, erase this part, which is the Gauss's law. Okay, for us to know the charges on the inner and outer surfaces, that is, these points, the charges at these points, and the charges at this point here. Good. Let's analyze this step by step. At this point, we can all agree that the electric field here is zero, or the charge enclosed here is zero. This is because the charges on this metallic conductor try to neutralize the charge in here, and we have excess positive charges outward. So, and this excess positive charge is Q1. Good. So now we need to keep in mind that this metallic conductor as well has an effect on these charges surrounding the first metallic conductor, right? So if here is positive, there will be negative charges here. This will automatically have like a negative Q1 in here to neutralize the positive Q1 outward, right? So, and with this, what we'll have outside will be both the positive Q1, Q2, which is due to the excess charges on this metal, and the positive Q1 as well. So in this case, so if we have Q1, right, because we have this Q1 because the metal itself will try to neutralize the positive Q1 here, right? So, and the negative Q1 will now act on this, thereby leaving behind the positive Q1 outward as well. So, and originally we know that we have positive positive Q2 due to the excess charges surrounding this metallic conductor. So therefore the charges in here will be minus Q1 for in the inner. The inner part, we have this to be minus Q1. And for the outer part, we have both Q1 and Q2. So the outer, we have both Q1 plus Q2. This is outer. So thank you for watching this video. I kindly like the comments if you like the video, if you actually like what we did, and if you have any question, feel free to send us email at nesalefaacademy@gmail.com.